Hello, everybody. It's a joy for me to be here. Hello, welcome to this first lesson from my side. I start to film here. I think nobody's on the film except me, so I have to locate myself a little bit in front of the presentation. But you can also download it from Moodle, which you see it. And the topic of today is bias-variance trade-off, which is the main topic here, because we have to adapt our learners to the data we have. There's always a trade-off between model complexity and data that we have. And it's called the bias-variance trade-off. We want a learner to adapt to this data, to generalize well on unseen data, the new data that we have. That is actually the ultimate goal of our learners. And yeah, in principle, this is our target. We really want to hit our target as good as we can, but then sometimes there's some side wind, you know. And although our arrow is pointed quite directly to the target here, there is a systematic shift, an offset, and we will call this a bias. And we don't hit the target anymore. If there is really a big wind, you know, the arrows start even to spread out a little bit, and there is additionally to this bias an added variance. We're going to hit the target even if we would be pointing here directly. Yeah? This is what there on the topmost right side is depicted when we have high variance and high bias. What this exactly means here, we can define it statistically. What is the bias term of our estimator? Estimator is an estimating function. It can be a classifier, it can be a regressor. We estimate, and we never know the true function here. True function is just given indirectly by the data. We want to have an estimator that has a minimum offset from the true values. So that the expectation value E is minimum. But the second thing is we also want the spread of the data to be smaller compared to measured data. And that's called the variance. It's the second moment of the statistics here. It's the squared distance and expectation value of that. So we want to have both of them. So, yes, okay, what is the goal of today? The goal of today is first of all that you know how to debug learning algorithms. It means how to learn a learner really in practice. Huh? Sometimes it's hard, you want to achieve some accuracy of your learner. You don't have it, but there's no reason to give up. Huh? There's a step-by-step procedure how you can improve your learner. Huh? And the best thing is just to start with this. Make a pipeline that works, not perfectly, and then statically improve it, steadily improve that one. Then, what we also see is that we can easily add complexity to a learner. For example, if you have a polynomial fit to data, you can increase the number of the degree of the polynomial. By doing this, you add complexity to the model. You add parameters that you have to estimate. And the more parameters you have, the more difficult it will be for the model to estimate it. Or on the other side, you need more data to really be able to determine that. And there's a technique which you can apply, and a lot of learners have this already intrinsically in. It's kind of a regularization. It's a penalty that we add to the loss function that we globally want to minimize. So there's always this trade-off, and the trade-off is also given or represented in the loss function itself. And the learner will try to make this trade-off automatically. Okay, and the topic of the exercises will be learning curves. What is this? This is really a good diagnostics for estimating the performance of our learner. And then deducing what are the necessary steps to do next to get a better performance. Huh? So this is a hands-on how we can improve the accuracy or minimize the error rate of our learner. generally, if you have any question, you can just raise up your hands and ask directly. If you don't understand anything, it's quite a direct talk here. You are part of it, and it's your lecture. So take a chance and ask also the questions. Good. Just for the overview, where are we? Basically, we're still, I would say, we start today here in the supervised learning section, where we have two types of learner. This is classification on one side, where our target, our response is discrete, is nominal, as discrete values, which we call classes. And one idea of this classification is predict the quality of a tomato given a photo of the tomato. It's impossible. Given a photo, the weight and, for example, the stiffness of the tomato. And we can decide, okay, it's a class A1 tomato, or the other one is rotten. We should throw it away. Regression is actually predicting a continuous variable out of the features, out of our data matrix. Continuous means it has really many classes, 2 to the power of 64 if you are in float 64 or something like that, or in a binary. And we try to model continuous, several continuous outputs given input vectors, which we call feature vectors, x1, x2, x3. What we will also look together in a few weeks is unsupervised learning, where we don't have labels, we don't have class labels, we don't have a given data curve that we want to fit on. It's just data, and we don't know what to do with it probably. But one idea is, for example, we have an image database of your friends or of 1,000 people, but you don't have any names, there are no labels on it. What can you do with it? You can detect, for example, similar pictures and say, okay, look for all people that have a beard, a beard. Look for all people that wear glasses. For this, we don't need additional information. The information is coded already in the features of the image. We just have to find the right features. All we have to teach a learning algorithm is how to evaluate, how to find the relevant features of this image. Clustering is then a way to represent, for example, high-dimensional data, and high dimensionality is also one problem in machine learning that we have sometimes a lot of parameters where our models depend on, but we don't have that many data that we could sample all instances of this model. This is called the curse of dimensionality. That we go higher in dimensions, actually, we would need exponentially more data. And at some point, it's just infeasible because it's too costly. There's not enough time on Earth to do that. And there's another exercise for today which takes into account actually the curse of dimensionality. And what we see here is also a way to reduce dimensionality. If we have too many features, we can take the most important features out, probably as a linear combination of all these features, to work in a subspace of this feature space, which is only low dimensional. And then the risk of overfitting is much lower. This is a good way to do it. And then another very nice thing is reinforcement learning, where we actually say, yeah, we give you sugar if you're good, and we hit you if you're bad. Normally, the learner gets a hit, the agent, but sometimes it gets a good point, it gets a, for example, in a chessboard play, most of the plays are bad, but some are good. The really difficult thing there is how would you judge actually one step of a play in a chess game when you only know after 50 pieces of plays that this was a good one. This is the most hard one actually for reinforcement. But there's a way to estimate the reward for every step that you take. But you have to do it repetitively, many times, so that you can learn how really to play good. It's another way, and here we are on this side, supervised learning, regression, classification. This is actually where we are today. Good. Yes, bias-variance trade-off. I will talk a little bit about PAC theory. PAC is such a nice name. It's called probably approximately correct. And for me, actually, this is You can hardly express some uncertainty softer than that. So there's a probability that we are probably approximately correct, but it's the best you can do in learning field. And there are two sides. There's a good side and a bad side. The good side is, okay, given some data, we can really limit how good we are. And on the other side, we know that for a given task, there's always a learner that can fail on that. There's no guarantee, there's no free lunch, so we have to try it out. And how do we try this out? We do it by a grid search. Has anybody ever heard of a grid search? Yes? Can you explain what a grid search is?
You validate a model with different, so you make something like grid out of your data, and then you validate your training data with that.
Right, exactly. So every model has some hyperparameters, we call them. Intrinsic parameters that are not given. We have to put them a priori, actually. And what you do is you just systematically loop through a certain range of these values in a grid. That's why you don't have the time to do it continuously. So you take a grid for all these parameters and you look for the best performance of these parameters given the validation set, or the test set, exactly. That's also what we will do in the exercises. We'll go through a set of parameters, which are called hyperparameters, which control this bias-variance trade-off, which control the complexity of a model. And to put them right, we have to do a grid search on the data we have. Okay. Cross-validation is that way, only way I would say, to really estimate the performance of an estimator of a learner in a statistically correct way. It's the best you can take out of the data if you take actually bootstrapping samples out of what you have and do it many times with different subsets of the data, check what's coming out, and then you make a statistics of what's coming out. Because all the parameters that we estimate are not just given numbers, they're normally actually distributions. There's not one value. It depends on the samples that you take of your data, what value you get for a certain parameter in a parameter-based model. Okay, learning curves, this is also what we have, and regularization, Rich and Lasso, probably you've heard of that one. Funny names. Behind these names is just two different ways to normalize the thing. It's the L1 norm and the L1 norm and the L2 norm. For a penalty, we add to the sum of errors, for example. Good. One example, and I think this is a intuitive example, because this we have done in school already. Fitting curves to data, one dimensional. And if we have this data given, which curve would you say fits quite well to the data? Just from your eyes, what would you select? Sorry? The middle one, right. Why wouldn't you take this one?
The arrows are quite big.
Yeah, there are some systematic errors, and you can even not give us the curvature of the curve. So there's something different here in the model. It's a curvature. The second derivative of this curve is not zero. So our model, if it's too simple here, just with order one, a straight line, cannot give you this dependency on the data. On the other hand, this one, it fits perfectly, actually, the training data, the crosses. And so we would say it's a perfect fit. What do you want more? The error is zero here, if I count it up. The error between my estimate and the given data points is zero. So we're happy, right? But imagine now that we sample a point here next time. We make a new measurement. And it's in between here. So the value that we estimate would be somewhere in the ceiling. Thousands units up. And that's why the variance of this model is very big. It's hopelessly overfitted. And somewhere in between lies the best fit. It's a smooth area where we want to be, where actually the complexity of the data, the structure of the data, is reflected on the other side by the complexity of the model. And that's how we want to look for that. Yeah, how we do polynomial regression. I will work a lot with Python, and I give you concrete Python examples because my conviction is that doing it in Python or some other one, but doing it directly is the best way to learn it. Huh? We're also learners, and doing it, training it on that, I think is a good one. Have you ever heard of a pipeline in paper? Pipelines are really practical because you can stack different steps of processing. Different learners you can stack. You can add the pre-processing step, for example, a scaling of the data, which is very often very necessary, with the training of the data, the fit procedure, and probably even then, if you want, that evaluation. Polynomial features here. If we get that from the pre-processing unit, what does it do? If we have features given in columns 1 to n, or let's say 2, we have 2 features, the length and the width, the weight and the height. If we generate polynomial features of that, what will you get? Polynomial features of degree 2 of this length and height would be, we first get a constant, which is the offset term, the bias. We get the length itself, we get the height. Then we get the product of height and length. We get length squared and height squared. So it generates all these columns. It's a way to generate features out of given features, which are linearly independent of the given features, because a square is not linearly dependent on an x squared. So we can generate many more features out of a given table of features. And that's how we can also add complexity to the model. If we generate out of given features new features, one way is just polynomial features. There's only one way. And that's the way how we would do it by fitting it. Of course, there are other methods which directly fit the curve to the data, like the polyfit of that NumPy also. But that's more the way how the machine learner will do. It's like, oh, let's generate some features. And then let's get the linearly dependent parameters for each of these features after they have been normalized. And then I can look at these feature parameters, theta 1, theta 2, theta 3, compare them and see how important is one of these features. Probably I can make, this would be a manual work, but later we do it automatically. We just kick some features out that are not relevant. Or features that are linearly dependent, we don't want to have. We kick them out. Okay, so in this graph actually, if we increase model complexity, what would happen on the error with training data? The model would be able to better and better fit to the data, so that error would decrease. It would decrease until it gets 0, when every data point is really matched by extent. But on the other hand, what then happens to the unseen test data, which is sacrosanct, you shouldn't touch it. It's hidden somewhere. At the end, you take it out and say, okay, now let's test. This is the hard test. What we test? The test error would also go down up to a certain model complexity. And then it would start to rise, and that's the moment actually where this variance starts to reign, to gain the overhand of the error. And then we have to stop. Then we just lose. The best spot would be here, or probably a little bit overfitting, a little bit only. I hope that we probably get some more data to avoid that. And that's where we have to stop. Because we cannot be better than that. Otherwise, we try another learner, another model. Then it looks again a little bit different. Okay. And the complexity we can control over hyperparameters, as we will see. For regression example, if we add a penalty, which is proportional to the length of a parameter vector, we can actually put the weight on this penalty. Given effect. Okay. This, when we have high bias terms, this we call underfitting. It's like a systematic error that the model cannot cope. Overfitting means actually high variance. The model complexity is much, much higher than actually the data would suggest. We can fit the training data perfectly, but the generalization error, this is what really counts because it's then in real life, gets worse. Okay, one nice thing is, very often we take as a loss function the squared error. Like in linear regression, it's the sum of the squared errors. This is a nice property because we get an analytic solution for it. It's a linear equation that we can solve, the normal equations, and we get the optimal parameters. If we go now from a loss function which has this quadratic form, we can always decompose that one in a bias term and a variance term and an irreducible error, which is really the stochastic part of a model, which we don't know about, which we cannot know anything about, because it's either the process behind it is so complex that we don't know, have any clue of it, or it's a real random process, like an atomic decay or something like thermal processes, which we cannot control. And that's why this is called the bias-variance decomposition. Now you see how the error is set together. It's always a bias part squared plus a variance part plus an irreducible error. This is, for example, if this doesn't go to 0, we have this kind of irreducible error. We cannot reach 0. On the other hand, here the bias term will be big. Here, actually, the variance term starts to be big for the test error. And you can prove that. I put it in the lecture notes. I don't want to go through. It's just how do you calculate these expectation values. I put the rules here, and then you can prove it. The expectation, for example, of a square is the variance of x plus the expectation of x squared. And for a linear function, which is here deterministic, it's just expectation of this deterministic function. It's not a stochastic function. Our real true function is deterministic. It's no stochastic. And then you can prove, okay, for me it's only important that you see, okay, an error can be decomposed in a bias term and a variance term, and an irreducible error. And we can graphically, using learning curves, actually get a clue about what the bias error is and what the variance error is. And then we know how to deal with it. Because if we have high bias, we have to increase model complexity. If we have high variance, we have to reduce it or at least add more data. For example, then the model can show its complexity. Is this okay? Speed is also okay? Good. So it's just algebra. Now, because I like it, this talk idea here is just a repetition. I just want it to be exact ones. It's not that you have to learn this by heart. It's not the idea. But often you've probably heard of this no free lunch theory. It comes actually from economics. Milton Friedman says there's no such thing as a free lunch in economics. You always have to pay for it. If you didn't pay for a lunch, you will pay later. And the idea behind this is actually that one. We have to start with a packed learning theory, and it's the theory of probably approximately correct learnability. And like in proofs in mathematics, probably you've heard, if something is smaller than epsilon, the other one, the output is smaller than delta. That's the idea behind it. For example, for a continuous function, if x and y are very close together, also the function values will be close together. And this idea is taken also here over by the Puck theory. And the idea is, first of all, we have an ideal learner. The true function, it's called here for a binary classification, the true labeling function, which knows for every part exactly what the true label is. And the idea is here we have it over the global data set. There's not more data, so this is really the truth we never will attain. What we call here, this is the loss function over this domain with a given true function, and this will always have an error which is 0 on this data because it's the true one. And what we can attain is just an estimate of this true function because, first of all, we don't have the full data set, never. So it can always be a subsample of it. Huh? And we don't know the exact structure of that F. So the best thing is what we can do is, this is called empirical risk minimization principle, to say, let's minimize the loss on the data we have with a learner, which is also called a hypothesis, that we have, that we guess. It's the best we can do. We don't know the truth, we don't have all the data, so we take one learner after another, one sample after another, and estimate this empirical risk and say, okay, we take the learner which performs best out of it. Now the bad story is here. That's the no free lunch theory. There's no universal learner. No learner can succeed on one learning task as formal as like this. This is now a little bit theoretical, but it's amazing. If you give this learner a little bit less than half the data, you can always construct out of this data a subsample where this learner performs really bad. Where the estimate here on the given data set, the loss function is bigger than 1/8. These are just numbers that say you cannot be better than that. And there's always a subset of data sets where this learner, this specific learner that you chose, will fail. You can find it. It's probably hard to find it, but there is a subsample part of our data set that will provide. So it's a little bit theoretically, here is X, actually this is the domain, and X here in vertical lines, this means actually the magnitude of this set. So how many elements does this set have? So we take a little bit less than half of the samples, and then we can prove that. That's also why we have to train, and we have to test, and we have to do grid searches even over learners, right? Because we cannot a priori be sure that, yeah, a small actual machine will perform best here. Right? There's no one that gives you that guarantee, because it depends on the data. Now the good message behind that is this one. Right? You can also create, but these are very conservative limits. Now you can turn it around and say, okay, to perform well, what do we have to do? One thing is actually, if we want to have a learner that will be probably, this means with a confidence of 1 minus delta, delta can be 2%. So in 98% of the cases, it will be approximately correct. What means correct means up to an error of epsilon. Then we have to get as much sample as this and train it in an intelligent way. And the nice thing is this is the hypothesis class. That's where we actually take our parameters from, our models from. If this is a finite class, it can be huge. The number of samples we need only grows logarithmically. It could be worse. It could be exponentially. So the logarithm gets flat. And although this margin is normally very, very overestimated, it's much overestimated, we get the tendency that we say, okay, we don't need exponentially more data in that case, logarithmically more. This is an I thing. And you see, the more confidence you want, the higher this one gets, the more accuracy you want from the learner, also the higher number of samples you need. And that's what you pay. That is actually the other side of the free lunch theory. PAC, probably absolutely approximately correct. The Bias-Variance trade-off can also be summarized by a monk. It was summarized by a monk, a British monk, or an Anglo-Saxon monk, you would say. His name was Ockham, William Ockham. And he says, actually a theory or a hypothesis should not be more complex than necessary. If you have a thing that you can explain by 2 ways, and one theory is very complicated, take the simpler one. Because it is the theory that will generalize better, because it needs less assumptions on these parameters. One good example for me is actually Newton's laws. Newton's laws of the planetary motion is one law actually that you need You have a mass in the middle, the sun, and planets orbiting around, and nothing more. You have just Newton's laws of gravity, and mass times acceleration is the sum of all forces. But in earlier times we had this geocentric view of the planetary motions. And to explain these complicated motions of the Mars and the other ones, the Jupiter moving forth and back from the Earth, you know, you had to make a theory which was very complicated because the Mars had to cycle like this around and Jupiter like this. Huh? And for this theory, you needed much more assumptions, and it turned out to be wrong because we live actually in a heliocentric world. Okay, and this is actually the guidance. We should not put more complexity in the model that the data give. Okay, generalization is decisive. It's most important. This is what counts. And how can we estimate how good a model will generalize? Here, the Merkel's cross validation. In statistics, we would just say, you have a bag with some small balls inside, and you can take out of it a sample and put them back in a different way. And you do this 20 times. No? It's also called bootstrapping. It's a way to separate out or to make groups out of our test data to retrain our models. Generalization is really what counts. And we have to find an acceptable, whatever it means. This depends actually also on the application. It depends on what accuracy you want from this learner. What is given by your boss who says, yeah, you know, I have to classify this with 1% accuracy because every misclassification costs me $1,000, something like that. It comes also from there where you have to stop or where you have to continue. So it's actually a requirement just from the top, what you want to achieve at the beginning. And this, you have to be clear at the beginning, what do I want? And what is the necessary accuracy for my learner that we succeed in this business? That we don't generate, that we generate money and that we don't lose money, for example. This is the first thing you have to think about. Okay, what is cross-validation? I think Tilo told you that a little bit also already in lecture number 3, but we'll go a little bit into that in detail. Normally we have a given data set, and it's a good idea to separate it in a test data set and a training data set. And later on, we will never touch that until the end. And what we do here is we separate the training set again in a validation set and again a training set. And using actually this cycle, it's also called the inner loop, we determine the hyperparameters of our model. Actually, if it's a parametric model, we determine these parameters for different given other hyperparameters. When we do this in a repetitive way, this could be actually a grid search that runs inside here. Once we have done that, over the whole grid search, we know the best parameter set on this given data. With that, we go out and say, this was the best we could achieve over this test validation set, so let's try it now on the test set. And this gives our generalization performance of the learner. This is then the final performance estimate. You're not allowed to change your parameters anymore. What you can then do is probably put all together and do a last estimation of the performance. But this one already is a little bit biased, let's say. So we have to split the data, and there's in scikit-learn a new a nice thing. It's test train split, an automatic thing that you can use for separating out high-dimensional data sets. And you can give actually, for example, a quantile. How much do I want to keep for testing? How much do I want to keep for training? You just give this in a percentage number. Okay, 0.2. I want to keep for testing. Yeah, it means just separating out, and of course, you have to look at this, that it is a stratified sample of your test data. It's not that you can take just the last 15 entries. Normally that's a bad idea, because sometimes there's a temporal dependency in the data, and then you would only get the last 50 points of a temporally dependent sequence, and of course then you would fail. So you have to take care that you do this sampling correctly. And stratified sampling means that you look at the distributions of the, for example, labels that you have. Some are very sparse, are very rare. Others are really make up the big chunk. And you have to do actually a stratified sample that represents the data set in a small fashion, what you have from the full data set. It's called stratified sample. So we would sample all out of our sample size. Yes, here. Test, train, split. That's the way to do it. Okay. And this is now a twofold cross-validation, where we say, well, let's do it once. We split the data in a training and test data set. We train everything on our train data set, and then we do once, actually, an estimate of the overall performance on the test data set. This is suboptimal. What are normally good sizes? I would say 80, 20% for training. 80, 90% for training, the rest for test. So typically it's like 3/4 to 1/4. This is normally how to check. Okay. Model selection is actually the selection of the hyperparameters. And this we do in this inner loop over the training data set. And we define first a range of our hyperparameters and determine it just, it's really sweaty. The computer has to work. There's no guess that you can say this is a good parameter or not. You have to try it out because the data is every time different. And then you fit every time the thing on the validation data and the final performance you test on the test data. Yeah. What are hyperparameters? Probably you can help me also a little bit here. Let's do some repetition. One simple learner is KNN. You know KNN? K nearest neighbor. Ever heard of? Who has ever heard of? K nearest neighbor. KNN. Let's call this our learner. I know this won't be on the video, but you have a look at it now. Okay, and this is the learner. Which hyperparameters do we have? KNN. KNN can be a regressor, not an aggressor, a regressor, or can be a classifier. So it selects actually out of a given set of data points, actually, I give a new data point, it looks in the neighborhood and makes a majority vote over the labels in the majority or the values. It's really simple. It's called, is this KNN, is this a parametrized learner or is it an instant-based learner? What would you say? Ever heard of these two differences? Okay, do we have to determine some parameters here? Like in the polynomial model, do we have to determine slopes and biases and offsets and so on in KNN?
Yeah, you have to define how many labels you want to.
Right. But this is not, you cannot do this by a fit procedure, right? It doesn't come out of the data. You have to give it in from outside, so it's a priori. And this is actually the K. The number of neighbors. Nearest neighbors. The number of nearest neighbors is here a hyperparameter, yes?
I don't know if it is a hyperparameter, but you can also favorite the neighbors that are closer to the point you choose. So you can favorite depending on the radius.
Right, exactly. This is another way. I would call this the norm you select. How do I judge the neighborhood? You can, the distance, what counts? Is it the closest one? Is it an average of the other one? Do we count actually an Euclidean distance? And so we can also, there's another one, we can actually select the matrix. The distance measure, L1, L2, L infinity. So we at least have two such hyperparameters which we have to give in, and when calling the instance, or when generating actually the instance, we have to define. We want a K and N classifier which looks at 5 neighbors. Why is 5 better than 4? Is it better than 4? We don't know. We have to test. But uneven numbers have the advantage that
They have to choose one.
yes, they have to choose one. There's not a pair situation. 2 say this, the other 2 say that. What do I do then? Right.
What do you stand for?
Nearest number of nearest neighbors. So it should be. Now, what happens if I increase K? What happens with my errors? What happens with the variance and the bias? Just think a little bit. I make a nearest neighbor classifier. Now I increase the neighborhood. And more instances are counting on actually what I classify for an unseen sample. What happens with? Yeah. So the bias increases, right? We get smoother. We get smoother limits between the classes. It's a smoothing because we average over more and more voters around. So this means actually we reduce the complexity of the model and the bias increases. So we could say here when K increases, complexity decreases, bias increases. Okay, let's take our polynomial model. This is now a regressor, polynomial fit, and the parameter that we can. Do you see that? It's okay? You see? The hyperparameter that we can choose is now the order. Let's call it also K. Order of the polynomial. So this is sometimes called theta_k, xk, something like that. This is our estimator f from x, and up to order k, where then I have to choose here j. And we wanna, and j starts with 0, so we have also the bias term. Yeah, if you increase the complexity here, the order k goes up. The bias will go down, the variance goes up. At least tendency. What about random forests classifiers? Random forest regressors. Last time you've heard, or 2 weeks ago, the concept of random forests, right? These are normally quite complex ones. They have enormous complexity. They're easy to understand, but they can fit almost any data. And here it's really important that we have means to reduce this complexity. So what do you think are parameters that control the complexity of a random forest? Of an ensemble, so we can also put the ensemble here.
Oh, that's the random forest. How does the random forest work?
So you've never heard of that, random forest? That you make a tree, a decision tree?
No.
Okay, then I'll come later with that, right? I thought, okay, but you have heard of ensembles, right? That you put different learners together and average over these.
We had that
But
with Tilo. We had it with Tilo last week.
I think so,
Two
yeah.
weeks ago.
Exactly, yes.
the ensembles, but also the tree.
And also the random forest.
Right. Okay.
Just the
A small one. Huh? When you make a decision trees where you select one by one a feature and say, okay, what is the best feature to decide now between this class and this class? Then you go a step further and so on. And normally, what you generate here is a tree which splits binary, given on different features. And every time you have a decision based on the criterion, like for example the entropy or the information gain, you select the best possible feature to separate out different classes. And these trees can grow very, very long. And at the end you can sample every point and you can classify it correctly on the training data. You know? So the idea is here that you can control the complexity. Is actually, there's one way to say I limit the depth of a tree. I limit the number of leaves. So these are already the parameters. Even graphically, you can probably understand now what is meant by this. So I would say the number of leaves, the level, how deep do I go, number of splits also here. Huh? And in an ensemble, and this helps now to average out, huh? You can select how many trees do I want to generate and make a majority division. Huh? So the number of trees. Even more. But let's leave it by that. Huh? Here we would see, okay, the more